Welcome to this new video where we will solve the spiral matrix problem. We have a matrix of size n by m, and starting from the top left cell, we want to traverse it in spiral order. We start from edges, then we keep going inside, as you can see in these examples. Elements we traverse should be returned in an array. Let's analyze this example and try to understand how can we achieve spiral order traversal. First, we always start from the top left cell, so our initial position will be 0, 0. Also, we always go to one of the four directions, up, left, right and down, so we will have a variable that tells us how much we add to our current I and j position to go to the next cell. For example, to go to the right, we have to stay on the same row and move to the next column. The value will be 0, 1. We will have -1, 0 for up, 1, 0 for down, 0, -1 for left, and 0, 1 for right. Another important thing we can notice is that we start by going to the right, then down, then left, then up, then again right, then down, and so on. We deduce that we can get the next direction starting from the current one. If we're going to the right and we stop, after it we need to go down. If we're going down and we stop, after it we need to go left. If we're going left and we stop, we need then to go up. And if we're going up and we stop, after it we need to go right. We will have a kind of map to know next direction. Okay, but why are we even stopping in the first place? Let's traverse this example in spiral order to understand. We start from top left cell, and the initial direction is to the right. We move by one cell, we can still move, and here we cannot continue to the right because we'd go out of border. This is why we switch to the next direction, which is down. We go down, and here we cannot go down anymore, so we turn left, borders. We go left, then we cannot continue further because we'd go out of borders, so we go up now. We go up, and here we could continue going up, but the next cell is already visited. We switch direction. After going up, we'd need to go to the right. We go right, and we cannot continue because the next cell is visited. We switch direction. We go down once, and we cannot continue. Next cell is visited. We switch to left direction. We go left once, and it's the last unvisited cell. We stop and return the result. From this example, we can deduce that when moving towards a direction, we stop in two cases, when the next cell is out of borders or when it's already visited. Let's try to implement this solution. We have as parameter a matrix, we store its dimensions in two variables n and m. We start at the top left cell, so I and j start at 0, 0. And initially we go to the right, so the initial delta is 0, 1. Then, we need the map from where we can extract the next direction. Right maps to down, down maps to left, left maps to up, and up maps to right. We also need an array traversal to store elements we traverse. It's the array that will be returned as output. We start by putting the value of the top left cell in it, matrix of ij, and we set it to null to know that it's visited. Now we keep looping to perform the traversal. We stop when our traversal contains n by m elements. It means that we traversed all cells. This is why we write while len of traversal smaller than n times m. Inside it, we start by calculating the position of the next cell. The amount with which we shift I and j depends on the direction. Delta I is delta of 0 and delta j is delta of 1. And the new position is I plus delta of I, j plus delta of j. Here we have two cases. Either the next cell is out of borders or already visited, in which case we should switch the direction, or it's safe and we can go to it. In which case we update I and j and add the value to traversal array. Let's handle both cases. The cell next I next j is out of borders if next I is below 0 or over n-1, or next j is below 0 or over m-1. And it's already visited if matrix of next I next j is null, because we're setting every visited cell to null. If one of these conditions is true, we switch the direction by using the map. We assign direction map of delta to the current delta. Else if it's safe, we update I and j by their new values next I and next j, we add matrix of ij to traversal, and we set it to null. After the loop, we return traversal, and we solve the problem. For the time complexity, we get an of n times m time complexity because we're just traversing an n by m matrix. We've reached the end of this lecture. I hope that you understood the solution. Like and subscribe if you want to support the channel, and see you in the next one.